Swayam Prabha. Digital India. Educated India.
Now, there are two ways by which you can think of randomization. Now, one way is just like there are two ways of which you can think of any dynamic game. One is through the normal form, the other is through the extensive form. In the normal form, we just list out the strategies and then think of the game as a static game in those strategies. And in the extensive form, we actually observe what the the flow of the information that is happening within the game. Now, randomization can also be thought of in these two different ways. The first way is that, well, you convert the game to a equivalent normal form, and then now in that normal form we have one way of randomizing already, which is that a player can pick a pure strategy from that normal form at random. Okay. This is what is called a mixed strategy, because that is what we refer to as mixed strategy in our in static games. Okay. So, first way of randomizing is choose a pure strategy at random. Now, pure strategies in a dynamic game are functions. So, you have a space of functions, set of functions, and you choose one of them at random. The probability distribution, or the probability with which you choose every function, is what is now the strategic decision. Okay. So, choose a pure strategy at random. Okay. So, this is what is called a mixed strategy. For a dynamic game. Can you tell me what would be the other way of randomizing?
By here we mean strategy of a single agent?
Yeah, so each player would choose a pure strategy at random. So what would be another way by which a player could randomize? So another way of randomization is the following: that whenever he gets to an information set, the player is aware of the actions that are available at that information set. He can choose an action at random at each information set. So, at each information set, he chooses an action at random. So, he chooses a probability distribution on the set of actions available at that information set. Okay. So, choose an action at random at each information set. And this is what is referred to as a behavioral strategy. Okay. So, the first one chooses a function at random. Okay. If a strategy is a function, so it specifies an action at each information set. So, at every information, so one of these functions is chosen at random. In the second case, we define, so in the first case, what we need to do is define one probability distribution, which is over the set of all functions, over a set of all strategies. In the second case, we need to define a probability distribution for each information set, but it is over the set of all actions available at that information set. As you can see, these are both valid ways of randomizing. A player may want to wait for an information set and randomize and randomly choose an action, that is the behavioral strategy, or he may say, well, here's my set of strategies, I am going to pick one of them at random. Okay. Now, the second one, which is the behavioral strategy, is something akin to a delayed commitment. Essentially, the player is waiting for the information to be available before he commits to a strategy, because the information, the probability with which he is going to take an action depends on the information set he is at. Whereas the first one is akin to a prior commitment, it's roughly akin to a prior commitment, because he is picking a pure strategy at random without waiting for the intra-game information to actually get realized. Is clear? Now, the question for you is there a difference between the two? Or is there, are these equivalent, is one the subset of the other, or one more somehow richer than the other? You can see both are very reasonable ways of randomizing. So, if one is a subset of the other, that is an important result, which basically it would tell us that, well, you can focus on one of these classes only. No, this is multi-act in general. In fact, in a single act game, this point actually becomes moot. The reason is because along every path, a player will play exactly once, let's say, and each such way of playing along that path defines for him a pure strategy, and that is equivalent to then picking the action in that information set. So, these actually become equivalent. I will show this formally, but but in fact, the point is moot in the case of a single act game. The point becomes interesting in a multi-act game, because now a player has to play multiple times. So, should he commit to a distribution on the set of pure strategies at the outset, or should he do a delayed commitment and play actions at random at each information set? Yeah. It's a strategy. So, it's a function that tells you what to do at each information set. That strategy is chosen, a strategy is chosen at random. It says that, play this action at this information set, that action at this, etc. So, based on the information sets, a definite set of actions are specified. So, for each information set, an action is specified, but the strategy as a whole is chosen at random amongst all strategies. So, related to this question, so you can see both of these are basically producing actions at random, right, but the mechanism for producing the actions is different. In one case, you are defining a set of strategies, which is functions from information sets to actions, which is telling you for what action you will be, each strategy tells you what action you will be taking at each information set, and you pick one such combination at random, right. That's a mixed strategy. In case, so effectively what you are doing is picking actions at random, but through these combinations you are picking a particular pure strategy, you are picking amongst the set of pure strategies. Whereas in the second case, you are being more explicit, you are choosing actions at random at each information set, right. So, somehow the equivalence of these two has something to do with whether these two in fact lead to similar or classes of distributions on your actions. Because if they did, then one way of randomizing would be equivalent to another way of randomizing, right. So, let me show you an example. It is actually true that these are not equivalent in general, okay, and here is a simple example to show this. So, let us start. So, consider this game. This was okay. So, here is player 1 starting here. Let us say he has two actions L1 R1. Then if he plays R1, then player 2 plays here L2 or R2, and player 1 now has to play again. Okay. But player 1 does not get to observe what player 2 has played out here. Okay. So, these two nodes here are in the same information set for player 1. The game can end in 5 possible leaf nodes. Let us just name these leaf nodes and let us see what can happen in each case. Okay, so let's call this outcome O1, this outcome is O2, O3, O4, O5. I am deliberately not putting numbers here because I do not want you to get distracted by the numbers. So, we have to just think of which outcome is getting realized, okay, so that then we focus on that rather than saying how much payoff each player is getting. Yes, it is a multi-act game. Player 1 is acting twice. No, it is not in feedback form. It is a multi-act game. It is not in feedback form. Yeah, that's a different. That's what I said last time, right? A feedback stage-wise feedback form is a very specific form of multi-act game. Multi-act is in general just not single act. Yeah, yeah. Okay. Any other question? Clear? Okay.
Can one call this that it's in feedback form by saying when you have stage 1 until P2 plays and then stage 2?
Yeah, I mean you could, but you could potentially reduce it to that sort of form. But I mean that's not the question here. I mean it's whether this can be. You could potentially add some fictitious action for player 2 in this stage, and then make it into feedback. Okay, but anyway, that's not our concern here. So if there are 5 possible outcomes, okay, and let us, what we will do is we'll allow players to randomize in these 2 different ways, all right, and let us see if we actually get some kind of parity between the 2 ways of randomizing. Okay, so first to begin with, let's look at let's write out the set of pure strategies for player 1. Okay, so I think I should write something here also for player 1. So this is again L1, L1, R1. Okay. Yeah, so let's write out what are the pure strategies for player 1. For player 1 has 2 information sets, the node that he starts with, and the second one is this information set, and at each information set he has 2 actions. Okay, so there are 4 possible pure strategies therefore. L1 here, L1 here, L1 here, R1 here, R1 here, L1 here, and R1 here, R1 here. Okay, so I'll just write these as pure strategies for player 1. I'll just write them in short as L1, 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 R1, R1, L1, and R1, R1. Okay, how many pure strategies for player 2? He has just 1 information set, he has only 2 pure strategies, which is to play L2 or R2. So what is now a mixed strategy for player 1? A mixed strategy for player 1 is a probability distribution on this set here, on this set, right, which means he is going to play one of these at random. Okay, so mixed set of mixed strategies. So let's call this gamma 1 and let's call this gamma 2. Set of mixed strategies what are the set of mixed strategies for player 1? It is, he has 4 pure strategies. So you can think of it as let's say y in R4 such that y is greater than or equal to 0 and it is a probability distribution, right. So it is a probability distribution on this set of pure strategies which has 4 elements. Clear? So it is specified by, so this set is every point in this set has 4 coordinates, okay, out of which 1 is redundant because this 1 transpose y is equal to 1. So you can say, well, this is, you give me, this is specified by 3 parameters. So a mixed strategy is specified by 3 parameters. Okay. What about the set of behavioral strategies for player 1? So, how do I define the set of behavioral strategies for player 1? So, in a behavioral strategy, he has to choose an action at random at each information set. Okay. So, there are how many information sets? 2 for player 1. So, at this information set, he chooses an action at random. Okay. So, he has to pick a probability distribution on this action set. So, a behavioral strategy will be specified by those by the probability distributions for each information set, right. So, at this information set, he chooses an action at random. Similarly, at this information set, he again chooses an action at random. Okay. So, a behavioral strategy then would be, say, he plays L1 with probability alpha and R1 with probability 1 minus alpha at this information set. And at the other information set, he plays L1 with probability beta and R1 with probability 1 minus beta. This is a behavioral strategy, right. So, every choice of alpha and beta between 0 and 1 will give me a behavioral strategy. Is this clear? So, do I need to say specifically what is the probability of playing this L1 and this R1 here? No, it is the same, because he has they will also be beta and 1 minus beta, because at this information set he has to play this as a function of just that information, right. Okay. Okay. So, the set of behavioral strategies therefore is specified by just 2 parameters, alpha comma beta. Now, this is immediately telling you something, right. The set of mixed strategies is specified by 3 parameters, right, and the set of behavioral strategies is specified by 2 parameters. So, we cannot really expect any kind of subset type relation like this, that one is a subset of the other or something like that, because these are now objects in 2 different spaces. Okay, these are fundamentally, I mean, there are more free variables in mixed strategies than there are in behavioral strategies. So, we can't expect a subset type relation, but we can. So, therefore, we have to talk of a relation between these that is beyond just inclusion, that one is a special case of the other.
Why is behavioral strategy not a subset of these strategies?
Because this is in R2. These are 2.
Beta plus 1 minus alpha 1 minus beta. This is a distribution, right?
It's a distribution, yeah.
So, it does belong to mixed strategy.
No. So, it's not a subset. What you are saying is that I can try to create a relation between the 2. Okay. So, that is in fact the point, that if you are looking for an inclusion type of thing where one is a special case of the other, then we have to ask special case under what notion, right? Special case under what notion, right? Because it is certainly not a subset, right? Then in what sense is this a special case? So, something has to be preserved under both type of strategies for you to get one as a special case of the other, right. So, this basically becomes the essential dilemma. Now, if you think about it, we have logically said that we could allow players to randomize in these 2 ways, which seem both reasonable, and it should be allowable that players be allowed to randomize in this way. But one kind of randomization gives a player who seems to be somehow not the same as the other. So, then we get into this position where we now have to choose. This is something which we would not want to do as game theorists, that we don't want to tie a player's hands and say that this is what he should do. We should allow strategic freedom to the player. Now, is there something that one can now still say that these are in some way similar or equivalent or interchangeable or whatever, right? So, this is essentially the juncture we reach, and now we have to come up with a way by which we say, well, is in what sense are these 2 strategies, comparable. Is it clear? So, yeah. Yeah, so that is part of the that's beginning. You are now beginning to think in that direction. Essentially, we have to think of, okay, what are we meaning by equivalent, right? So then you ask, okay, well, if it's equivalent from the point of view of payoffs, right? Then we can ask, okay, well, if one framework you can say is, well, I am asking for equivalence in terms of payoffs, which means that the payoff that I get, the expected payoff that I get under one, I should also be able to get it under the other by a suitable choice. Means for all mixed strategies that give me a certain expected payoff, can I produce a behavioral strategy that gives me the same payoff? This could be one notion of equivalence, because then in that case I don't care about whether I use, and as a player I don't care, and likewise as an observer of the game I don't care what the player is doing, whether he's randomizing this way or randomizing that way. But you can see there is one catch there as well, because the expected payoff depends not just on what this player is doing, but also what other players are doing. So then we have to define expected expected payoff as being the same in a very strong sense, that it means that regardless of what others do, this guy should be able to simulate the same payoff with two different types of randomizations, right? Yeah. On joint distribution and marginal distribution on? Roughly, yes. Yeah, correct. So you are absolutely right. Essentially, these two ways of randomizing, they define for you a joint distribution on the set of nodes of the tree. They tell you with what probability. If I tell you a mixed strategy or a behavioral strategy for each player, okay, whatever combination, some may play mixed, some may play behavioral. Effectively, it from there I should be able to compute the probability of the appearance of the probability that the game history passes through each node. For every node, I should be able to compute such a probability, right? So you are absolutely right. But then now I can compute that, but then now for equivalence, what should I ask for? So what Ashwin was saying was that you can ask for something. Can we start with the payoff? Let's just say, okay, let us just ask that the probability of reaching the leaf nodes is the same, right? But then we have a joint distribution which tells us the probability of reaching any node, not just the leaf node, right? So then that gives you that then demands us maybe should we be extending that? Why leaf node only? Should we be allowing for all nodes? If we allow for all nodes, does it become too restrictive, etc., etc.? These are all questions involved in trying to come up with the right notion of equivalence, right? So this question actually is actually very interesting, and it turns out it's related finally whether there is any equivalence between these two has something finally to do with memory. This issue comes up only in multi-ag games, and as I said, the fundamental new feature in multi-ag games as opposed to single-ag games is the issue of memory. What does a player know of what he knew earlier? Okay, and whether these two forms of randomization, this form of randomization or the other, mixed and behavioral, whether these two can be interchanged in an effective way is eventually decided by what a player can remember. Okay, so the memory has a huge role to play here. Okay, so what I'll tell you is this notion of equivalent. So the way so it turns out actually that if we restrict ourselves to only leaf nodes, right, here, If we restrict ourselves to only leaf nodes, it becomes too, let's say, one is, it does not become elegant. The other is, it also leads to a whole bunch of other loopholes, which we will have to plug later. Okay. So, a much better notion of equivalence is that you ask for equivalent, that you can simulate the same distribution for every node in the graph, for every node in the tree. Okay. What we will do is, we have now two different ways of randomizing. So, we will let sigma I be mixed strategy of player I. So, this is a probability distribution on, probability distribution on gamma I, which is a set of pure strategy, and Bi is the behavioral strategy, So, behavioral strategy is a conditional probability distribution now. Given each information set, it produces a probability distribution on the set of actions. So, it is actually a collection of conditional probability distributions. Okay. So, this is, so the way we write this is that Bi of this given an information set eta I is a probability distribution on actions available at eta I. Okay. And I will put in another notation here, mu I, this will stand for either of the above. So, when I write for all mu I, for example, it would mean that it could be, it is essentially all mixed and all behavioral. Okay, that is what it would mean. Okay. Now, so here is the definition of equivalence. Mixed strategy sigma I, a mixed strategy sigma I, and a behavioral strategy Bi are equivalent are said to be equivalent if for every mixed stroke behavioral strategy mu I, behavioral strategy mu minus I, strategy mu minus I, and every vertex x in the game tree we have the following: the probability of reaching the vertex under sigma I when player I plays sigma I and others play mu minus I is equal to the probability of reaching that vertex x when player I plays behavioral strategy Bi and others play mu minus I. So, notice how strong this is, but this is what we need, otherwise we will end up having too many loopholes to fill, as I said. Okay. So, this is strong. Why is this? So, we are saying that two notions, two types of strategies, sigma I is equivalent to Bi if for every thing that the others play, they could play mixed stroke or they could play behavioral, that is encompassed into mu minus I. So, any mixed or behavioral strategy combination that the others could play called mu minus I, and for every vertex in the tree, these probabilities are the same. Okay. So, what is this probability? This is the probability that you reach vertex x when player I plays sigma I and others have playing mu minus I, And this is the probability that of reaching vertex X when player I plays Bi and others play mu minus I. Is this clear? So, once I specify a profile of strategies, combination of mixed behavioral whatever, it produces for me a probability distribution on the nodes of the tree. So, these two quantities are well defined. What I am asking for is that regardless of what the others play, I should be able to get the same distribution, okay, that I get from sigma I, that I should be able to get the same one from Bi. Okay. So, this means that this makes these two strategies equivalent. Okay. So, I switch from sigma I to Bi, I should be able to get, if the distributions of probability distribution on the nodes remains the same and others and it remains the same regardless of what the others play, okay, then regardless of remains, I mean the equality holds regardless of what the others play. Okay. Of course, the distribution will keep changing with the choice of mu minus I, but when it changes to the same, the one that I get with sigma I is equal to the one that I get with Bi. Is this clear? So, now as a result of this, we get the following simple fact that if sigma I is equivalent to Bi, if the mixed strategy sigma is equivalent to a behavioral strategy Bi, then for all mu minus I, the payoff that a player or the cost that a player gets when he plays sigma I and others play mu minus I is equal to the cost that he would get when he plays Bi and others play mu minus I. Is clear? Now, of course, the value of the cost will depend on what others are playing, but regardless of what others play, I can get the same values by switching from Bi to sigma I to Bi. Is this clear? Okay. Right. So, and now this is equivalence between strategies of one player. If you have this way equivalence between the strategies of all players, right, then you would have that this is true for every player. Okay, every player will be able to switch from between behavioral and mixed.